This is the first video in BC Calculus over Taylor and Maclaurin series. And this is actually part one of Taylor and Maclaurin series. We're going to be looking at lots of different aspects of these particular series. And so there will be multiple days that we spend on this topic. So before we talk about Taylor and Maclaurin series, we're going to kind of review some things that we know previously from this unit that are going to help us out with Taylor and Maclaurin series. One thing we know is that we can represent functions as power series, and that we also know that we can then represent a power series as a function. That's what we've been doing with our power series recently. And so the most basic type of a power series is a geometric series written as the sum from n equals 0 to infinity of a times r to the n. And the sum formula would be a over 1 minus r, which is the format we use to come up with the function for the power series. And that power series or the geometric series will converge as long as the absolute value of the common ratio r is less than 1. And if it is greater than or equal to 1, then the series will diverge. So if we replace instead a with a 1 and r with an x, that's how we get our power series and our function for the power series notation from the geometric series notation. So that's the most basic power series right there. The sum from n equals 0 to infinity of x to the n, which is the same as 1 over 1 minus x in function form. So Taylor and Maclaurin series came about because what if we don't have a way of relating a function specifically back to 1 over 1 minus x? With all of our power series problems that we've been doing, where we've been given them in function form and then told to write them as a power series, we've had to kind of manipulate most of our functions to make them look like that 1 minus in the denominator. But what if we can't make that happen? So if that's the case, then we really kind of need a more general way to write a power series representation for a function, and that's where Taylor series come about. So for example, if we're given a function, and if you notice, this is the formula for a power series centered anywhere other than 0. So that's where that x minus a to the n comes from. And so then we've got the expanded form written out for the first few terms there. So the question then becomes, how could we figure out what those missing coefficient values, c sub 0, c sub 1, c sub 2, how can we figure out either what their values are or kind of where they come from? Well, what we could do is, what if we replaced the x here and in all the terms with an a? Well, if we do that, then f of a would be c sub 0 plus c sub 1 times a minus a plus c sub 2 times a minus a squared, and so on and so forth. Well, hopefully you realize that that a minus a in each of those terms, that's going to give me 0. So the c sub 1 term is going to end up becoming 0, the c sub 2 term is going to end up becoming 0, and so the only thing left would be the c sub 0. So c sub 0 is whatever my function is evaluated at that a value for my center. So if I was given the function, I would just need to evaluate it at my center, and that would tell me what c sub 0 is. Okay, so now I want you to kind of go with me. So if that f of x expression is the c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a squared, and so on, if I then wanted to find the derivative of that, f prime of x, I would take the derivative of each of those terms. So the derivative of c sub 0, since that's a constant, it would become 0. The derivative of c sub 1 times x minus a would become c sub 1 times the derivative of x minus a would just be 1. And then the next one would become, we would bring the 2 in front, times c sub 2 times x minus a would become to the first power. Okay, and then I'm going to put, we'll do a couple more terms up here. So I would have c sub 3 times x minus a to the third, and c sub 4 times x minus a to the fourth, and so on. So that means the next term would be 3c sub 3 times x minus a squared, and then plus 4c sub 4 times x minus a cubed. And so that would become the power series for f prime of x. And so if we evaluate that at x equals a, we get c sub 1 plus 2c sub 2 times a minus a. See what's going to happen there and see what's going to happen in every subsequent term? Those are going to go to 0. And so c sub 1 is equivalent to the first derivative of the function evaluated at a. All right, now go with me again. So then f double prime, if I go up here to my f prime of x expression and start taking the derivative of it, c sub 1 would go to 0. Then we would have 2 times c sub 2 times 1. Then the next piece would become 3 times 2 is 6, c sub 3 times x minus a. Then plus 12 c sub 4 times x minus a squared, and so on. So then if we evaluate that at the center, we get 2c sub 2 plus 6c sub 3 times a minus a, and so on and so forth, because all those terms are going to become 0. So it is 2c sub 2, which means that c sub 2, if I want to solve that, it would be f double prime of a divided by 2. So this coefficient could be found by evaluating the second derivative at a and dividing it by 2. All right, let's do one more. See if you can see the pattern. So now let's do the third derivative. So if I go up here to f double prime and take its derivative, 2c sub 2 goes away. The next piece becomes 6c sub 3, then plus 24c sub 4 times x minus a, and so on. So then if we evaluate it at a, we get 6c sub 3 plus 24c sub 4 times a minus a, and so on. So that becomes 6c sub 3, which means that if I solve that for c sub 3 is equal to the third derivative evaluated at a divided by 6. Now there's another way that I can write 6, and you're not going to like this, but it's in terms of factorials. What factorial is equal to 6? If I multiply a number times the one less than it, times one less than it, all the way down to 1, what would give me 6? Three factorial would. So if I go back up here to the top, this c sub 3 would be the third derivative evaluated at my center divided by 3 factorial. So I think we've done enough at this point that maybe, hopefully, you might be seeing a pattern for how we find these coefficients here. So the pattern that I noticed is that a particular coefficient, so we'll call it c sub n, would be the nth derivative. So for example, when I wanted the third coefficient, it was the third derivative evaluated at the center, then divided by n factorial. Because even the one that was over 2 would be 2 factorial, and the previous ones would be over 1 factorial, which is 1, and over 0 factorial, which is also 1. So this would be how we could find the coefficients for each of those terms for the power series. So that actually brings us to the formula for how we generate a Taylor series centered at x equals a for a power series representation. So a Taylor series is essentially just a special kind of power series. So the formula is that you evaluate your original function. So you would actually be given a function, and then they would say represent or find the power series to represent the function. So you would evaluate your function at the center, and then you would do the first derivative evaluated at the center times x minus the center. And then the second derivative evaluated at the center over 2 factorial times x minus the center squared, and so on and so forth. And this would be the formula for the nth term, which also means this would be the sigma notation for that Taylor series or that power series. You could replace those k's with n's. They mean the same thing. It doesn't matter. Okay. And then the partial sum would be if we only wanted a certain number of terms of the Taylor series. Sometimes the problems will just say, find the Taylor series or the Taylor polynomial of degree 4. So you would stop once you got to the x to the 4th or x minus a to the 4th term. So this will work for all centers A. If your center is 0, then that would make each of those little x minus a expressions just be, it would be x minus 0, or it would just be x. So this would be x squared, x to the n, all that sort of thing. When you're centered at 0, it's no longer called a Taylor series. We call it a Maclaurin series. So all they are is Taylor series, which are special power series that happen to be centered at 0. And there are some Maclaurin series that we just kind of know, which means you need to memorize them so that you can easily recall them. These are on the back of your cheat sheet, but they're also here in these notes as well. So we have the Taylor series representation for the function 1 over 1 minus x. We have 1 over 1 plus x. We have e to the x, sine of x, cosine of x, natural log of 1 plus x, and then down here, inverse tangent of x also. So what this means is that, like, if you don't have a calculator, let's say, and you need to evaluate natural log of 1 plus x, but you can't really do it without a calculator, you can approximate the function natural log of 1 plus x using a polynomial function, which is this Maclaurin series here. And the more terms that you pull into the polynomial function, the more accurate that approximation is to the actual function natural log of 1 plus x. That's why the concept is that n is going to infinity. If I only use like x minus x squared over 2, it's not going to be a very accurate representation of natural log of 1 plus x. But if I incorporate more and more terms onto there, it will be a more accurate estimate. And we will actually down the road talk about error in our estimates with these Taylor and Maclaurin approximations. So this kind of wraps up your introduction to Taylor and Maclaurin series in our first video here. The second video for part 1 is going to talk about actually kind of coming up with Taylor polynomials.